Hi everyone, it is Wednesday, so that means it is time for the Chem Help ASAP live stream. So hope everyone is doing well today. So this week, I thought we would go over quantum numbers and electron configuration. Now, before I start, I do want to say, because this is obviously a short live stream, we are going to be doing a simplified version of quantum numbers. And for our electron configurations, we're going to be focusing on the predicted electron configuration, so we won't deal with exceptions. We just won't have enough time to go over all of that. But I know that quantum numbers can be difficult for many students, especially the first time you see them. So I thought we would spend a little bit of time just doing a refresher. And then hopefully you can see how quantum numbers influence the periodic table and electron configurations as well. So let's get started. Okay, so there are four quantum numbers, and we're just going to talk about each of these in turn. So we're going to start with n, which is our principal quantum number. Now, n is going to give you the size, and it's also going to give you the energy of the orbital. So I will show this later. I couldn't fit it on this screen, but if you look at the periodic table, so hopefully your periods or your rows are numbered. Those numbers, those are the values of n. Okay, so that is our principal quantum number. The values start at 0 and move on up. All right. Next we have L, which is the angular momentum quantum number. Now, this gives the angular momentum of the orbital, but what it really does, what it does in the physical world and what helps us make sense of it, is it's going to determine the shape of the orbital. So when you have your value of L, when you determine your value of L, then you are going to know what shape of the orbital you're dealing with. And again, we'll talk about all the shapes, and I've got pictures of the shapes as well. And the values here are from 0 to n minus 1. Okay. Our third quantum number is m sub L. This is the magnetic quantum number. And this is going to give the orientation in space of the orbital. So again, when you see the pictures, this is going to make more sense. But it really relates also to the symmetry of the orbital and how many ways you can rotate it and get a different rotation. Again, it makes a lot more sense once we see the pictures, but I just couldn't fit everything onto one slide. The last quantum number is actually the easiest, m sub s. This is the spin quantum number, and it specifies in the orbital if you have spin up or spin down. So in an orbital, you're going to have 2 electrons, and they're going to have a unique set of quantum numbers, so we need to make sure we specify quantum numbers for those two. So our values for m sub s are simply going to be plus and minus 1/2. Again, this is why we call it spin up and spin down. All right, so those are our 4 basic quantum numbers. Let's put them in a table. It'll make a little bit more sense here. All right, so we're going to start with a value of n as n equals 1. So again, if you look at your periodic table, and again, I couldn't fit it on this slide, but if you look at your periodic table, this is going to be your first period or your first row. So this is the period that has hydrogen and helium in it. Okay, so remember, when you're calculating L goes from 0 to n minus 1. Well, when n equals 1, n minus 1 is 0. So there's only one value for L, and that value is 0. So once we know L, we can determine m sub L. Again, I'm going to go back and show this. So m sub L is determined by L, and its values are negative L to L. So in this first row of my table here, if our value of L is 0, then our value of m sub L, it's not going to go from, you could think of it as negative 0 to positive 0, but it just means it's 0. It's only one value. So our value of m sub L is 0. Now, what this means physically in terms of what orbital you're dealing with, you are dealing with the s orbital, and its shape is a sphere. So you can think of it like a ball in 3D space. So this is going to be the 1s orbital because our value of n is 1. There is only one one s orbital, and it can of course hold 2 electrons. Each orbital can hold 2 electrons. Let's go through this for just a couple of more rows. I'll show you some highlights here. We won't go through, we just don't have time to go through all of the rows, but I find this table very helpful. Okay, so let's go to a value of n equals 2. All right, so now instead of just having one value for L, we have 2 values for L. Remember, L is going to go from 0 to n minus 1. Well, n minus 1 in this case is 1, so we have a value of L of 0 and a value of L of 1. All right, let's go back to our value of L as 0. Let's fill in this row. You can already see what the numbers are, but again, the value of m sub L here is also going to be 0. Remember, m sub L is determined by L, and it's going to run from negative L to positive L. When L is 0, m sub L is just 0. So this is going to be an s orbital, but because n equals 2, this is your 2s orbital. So we are looking at not the first row on the periodic table, but the second row. This is the one that's going to start with lithium. All right, so in the 2s orbital, there are only one type of orbital. Again, it's a sphere, and you can fit 2 electrons into that one orbital. Let's talk about when your value of L is 1. All right, so remember, when n equals 2, L can be 0 or L can be 1. So when L is 1, we're going to have a different shape, a different type orbital here. Remember, your values of m sub L run from negative L to L. So it's going to run from negative 1 to 1, which means it goes through 0. So if you see there are 1, 2, 3 values of m sub L, these mean that you have 3 different orbitals, and these are the p orbitals. Now, because n equals 2, these are 2p orbitals. There are no 1p orbitals, because remember, when n equals 1, we only have one value of L. So these are the 2p orbitals. There are 3 of them. So if there are 3 orbitals, they can each hold 2 electrons. Then we're looking at 6 total electrons that can be held in the L equals 2 orbitals. So I hope this is kind of making sense here. What I want to do is, we just don't have time to go through all the rows, but let's go down to n equals 3, and I specifically want to point out our new value of L here. So we still have 0 and 1, and those are the same as they are before, but now we have a value of L that is 2. And when L equals 2, those are called d orbitals. They have a different shape. Again, I do have pictures of all of these that I will show you. So when L equals 2, remember, m sub L is going to run from negative 2 to positive 2. So that's how we get all of these values here. We're just counting from negative 2 to positive 2. We're just following the integers here. Okay, so that gives us 1, 2, 3, 4, 5 values of m sub L, which means we have 5 orbitals. Remember, each orbital can hold 2 electrons, so we have a total count of electrons for these 5 orbitals of 10. Again, these are the 3 d orbitals. Now there's one more type of orbital that I want to introduce, and this is when we get to n equals 4. So I've already talked about 0, 1, and 2 when for values of L, Now I want to talk about when L is 3. So when L is 3, remember m sub L is going to run from negative L to L. So it's going to run from negative 3 all the way to 3. So I have 1, 2, 3, 4, 5, 6, 7 values here, which means I have 7 types of orbital. Each orbital holding 2 electrons, that is going to give me 14 electrons in these orbitals total here. These orbitals are the f orbitals. Again, it's 4f because n equals 4. So our quantum number is tied very much to the type of orbital and the energy of the orbital and the orientation of the orbital. So this is how we get to our different types of orbitals. Okay, again, we are kind of glossing over, solving the Schrodinger equation and all of that, because again, it's just beyond the scope of what I can do in this live stream. But this is how, when you're given a value of n, then you can determine your value of L. You can determine your value of m sub L. And of course, your value of m sub S is always going to be either plus 1/2 for spin up and negative 1/2 for spin down. So this is how all of these numbers are interconnected here. And each electron is going to have a unique set of 4 quantum numbers. So if you specify 4 quantum numbers, then you have specified 1 electron in one particular orbital. And again, you've even specified if it's the spin up or the spin down electron. I don't know, maybe that's clear as mud. I hope that helps. Quantum numbers are definitely something that students struggle with. I would encourage you to, look at them, study them, take a break, come back to them. Sometimes this information has to percolate a little bit. Give yourself time with these. All right, so since there are either no questions or too many questions to ask, let me show you pictures of the orbitals here. So we talked about s orbitals, p orbitals, d orbitals, and f orbitals. So we'll start at the top of my little pyramid here. This is our s orbital. Now this is for 1s, for 2s, for 3s, et cetera, et cetera, et cetera. They all have the same shape. Now they're going to have different sizes. They're going to get bigger. But the s orbital is a sphere. So you can see, again, if you have a sphere, you can rotate it in space however you want, and it's going to look exactly the same. So if I took this sphere and I made you close your eyes and I rotated it and had you look again, you wouldn't be able to tell that it has been rotated. So going back to my table here, that is why there's only one value of m sub L. There's only one orientation here. It is a sphere. Okay, so now let's talk about our p orbitals. There are 3 p orbitals, and what I really want to be able to show you here is how they change when you rotate in space. So if you look at this px orbital, you can see the lobes of this orbital run along that x-axis, which is why we call it px. But if I were to take those orbitals, and it looks kind of like almost like a really, really simple balloon animal or a dumbbell, whatever shape makes the most sense. If I were to take those lobes and rotate them, you would be able to tell that I rotated it. So this is where we get PZ and PY. So you can see PZ, you've got the same lobes, but now you've rotated them in 3D space. You've put them along the Z axis. And of course, PY has the lobes along the Y axis. So this is where this orientation comes from. You can reorient all these orbitals and you'd be able to tell, no, you definitely changed that. Whereas again, the s orbital, you can rotate it and you can't tell a difference. So to go back one more, if I look at, let's just look at my 2p's, although this is the same for 3p and 4p, you can see I have 3 different values for m sub L. These are the 3 orientations of the p orbital. And that's why you have 3 values here, and we have 3 different orbitals here. Again, I want to show how these are interconnected, how they're linked, really, is what I want to say. So those are the P's. We want to talk about the D's and the F's. P's are something that maybe you can draw. I cannot draw D's and F's. So here are our 5 D orbitals. Again, why are there 5? Let's go back to our table. So when we have D orbitals, we have a value of L of 2. Now that gives us 5 values for m sub L, hence why there are 5 different D orbitals, and there are 5 different orientations in space for the D orbitals. So these guys, again, they'll make sense like the p orbitals. So let's actually look at let's not look at the first one, that's a little difficult. Let's look at this DXZ. So that means these 4 lobes are oriented in the XZ plane. So hopefully you can see how they're oriented in the XZ plane. But if I were to take that and rotate it into another plane, say for example the YZ plane, then I would get this shape here. So you can see we still have 4 lobes between these guys, but again, I've just rotated it in space. So that is why we have this DXY here. You have the 4 lobes, again, they're rotated in a different plane. Now, what doesn't fit quite so neatly is the dz squared. It's got a little donut in the center. Again, I'm not going to get into solving the Schrodinger equation at this point because I want to keep this really, really simple. But these are the 5 shapes for our 5 different d orbitals. Okay, so let's also look lastly at our f orbitals because I do want to move on to electron configurations. So here are our 7 f orbitals. Again, why are there 7? Let's go back to our table. If we look at our f's here, there are 7 values of m sub l. So you get your f orbitals when your value of L is 3, because that is going to give you 7 different values here, which gives you 7 different orientations of this orbital. Now, these are a little bit wild, and I definitely cannot draw these, which is why I used a picture here. So you can see these do represent how they're oriented on the plane. You can kind of see that some, but again, you get kind of interesting looking ones with this fc cubed. But there are, again, 7 different f orbitals, and that gives rise to the 14 electrons that you can put into the f orbitals. Now, the one last thing that I want to point out about these orbitals, especially the p, d, and f, is these different orientations do not change the energy of the orbital. So these are called degenerate orbitals. Let me actually write that down. These are degenerate. And it doesn't mean they're bad. It means that they all have the same energy. So your px, your pz, and your py all have the same energy. You just have a different orientation in space. So again, your p's, your d's, and your f's are going to be degenerate orbitals. They are all going to have the same energy. So let me show you what that energy looks like. All right, so I'm going to start here with, this is called an energy orbital diagram, or energies of orbitals. There are a couple different names for this kind of diagram, but it gives the different energies of all of the different orbitals. So you can see I started here with the lowest energy orbital, which is the 1s orbital. So if I were to go back to, this is our orbital here where n equals 1 and L equals 0. Again, it all ties together. So my lowest energy orbital is the 1s. Then next is the 2s. And if you remember, again, going back, once we have the 2s, then remember when n equals 2, L can also equal 1. So that's when we introduce the 2p's. This is how I am building up my energy diagram. I am tying it back to the quantum numbers. So I go 1s, 2s. Here are the p orbitals. So notice how I have 3 lines, but they're at the same point in terms of the energy on the y-axis. These are the degenerate levels of the p orbitals. Up here are my d's, and you can see I have 5 spaces for the 5 orientations of the d orbital. Now, I didn't make this energy diagram big enough to show the f's, but if you continue along, you can show the f's here as well, and there would be 7 spaces for them. The problem with using the energy diagram is it gets very large and cumbersome, but you can use it to show where all the electrons are in any element that you want. You just got to make sure you've got a big enough diagram for whichever element you're going to do on the periodic table. Something else that comes out when you map out the energies of the orbitals, and again, this relates more to the calculations and solving all of your equations for the orbital, so I'm just going to leave it at that. But what I want you to notice is like your 1s, your 2s, your 2p, your 3s, your 3p, like this is all very much following, our table here, right? But what you would expect after your 3p is to find your 3d at the next energy level, but it doesn't actually work out that way. So what you have when you're following your energies is after 3p, your next lowest energy is actually your 4s. So when you are using the Aufbau principle and you are filling your energy orbital diagram from lowest to highest, you will fill your 4s orbital before you fill your 3d orbital. And the same is going to be true for the f's. So we can see this in the periodic table. So remember, these numbers right here, these are your values of n. So this shows your principal quantum number. And you can see when n equals 1, I only have 2 elements here. And that is going to fill up my 1s orbital, and that orbital is full. You can't fit more than 3 electrons in an orbital because then you're going to have multiple quantum numbers for all of the orbitals. So you only get 2. You get 2, a maximum of 2 electrons per orbital. So to get more electrons, to get more orbitals, I need to increase my value of n. So I go to my n equals 2. And this is where I get my 2s orbitals. And here are my 6 2p orbitals. So again, remember you had 3 degenerate p orbitals, which gives you 6 total electrons. This is why there are 1, 2, 3, 4, 5, 6 atoms here, because you have added 6 electrons. Okay, so that takes care of our n equal 2. If we want to add more orbitals, we need to go to n equals 3 here. So hopefully you see that there is a pattern. Here are your 3s. Here are your 3p. Now, again, you're probably wondering, well, where are the 3Ds? But remember that your 3Ds are higher in energy than your 4s. So this is why you first see your Ds down here in row number 4. So there is a rule for this. If you're looking at the periodic table and you say, all right, so these are definitely my Ds, because again, you can count up, you've got 10 spots, you have 5 orbitals, they each take 2 electrons, so those are your 10 electrons. Ds are going to count back 1. So these Ds are in row number 4, but they are actually the 3 Ds. So I'm going to actually just write that down. So d orbitals count back 1. All right, so that means if I'm looking at the d orbitals and this period here, this row here, they're in row 6. That means these are the 5d orbitals. They are not the 6d, they are the 5d orbitals. The same thing happens with the f orbitals. Again, my energy orbital diagram is just not large enough to show the F's, but they also, their energies are different than what you would expect just based on the table with our quantum numbers. So your F orbitals are down here. Those are these guys all the way down here, your lanthanide and actinide series. And well, I've pulled lanthanum and actinum out. That these actually do not have F orbitals, but if you count from here to here, there are 14 spaces. There are 14 F electrons because there are 7 F orbitals. Again, if you remember to your values of M sub L, there are 7 of them, which means I've got 14 spaces. I can put 14 electrons in. Now, your lanthanide series, this is why they left the blank here, fits in right here. You can see it starts at number, well, not quite. It's named after element number 57, lanthanum. It is in row 6. But these F orbitals are actually your 4F. And I will go back and show this. So remember, when we first get to our F orbitals, this is when n equals 4. That's why these are the 4F orbitals. But on the periodic table, this is again due to the energy level of all the orbitals. These are going to be your 4F orbitals. So they are in row 6, but they are your 4F. So I'm going to add a second rule to my d orbitals count back 1, and that is F orbitals count back 2. Whoops, that is a K. Count back 2. All right, so these are the 2 rules you need to remember and how they correspond to the periodic table. Your D's, you're going to count back 1, and your F's, you're going to count back 2. And I'm meaning count back 1 or 2 from your principal quantum number, these numbers right here that are giving numbers to your periods or your rows on your periodic table. Whew, okay. Again, I don't know if there are just lots of questions or no questions at this point because it is very difficult. But this is why the periodic table has the shape that it does. And it's actually really, really handy as we start doing some electron configurations, because what you'll get as you get used to this, you'll be able to look at the periodic table and say, oh, I know what electrons those are. So if I look at any element in here, I know that they are going to have s orbital electrons. These guys here, these are your D's. Here are your P's, and here are your F's. So if you're ever in a test and you go, oh, the D electrons, how many orbitals do I have? I know it's more than 6, but I don't remember how many more. Well, as long as you know your D's are right here, you can just count across and you go, okay, there are 10 spaces here. That means I can put 10 electrons in my d orbitals, which means there must be 5 d orbitals. So your periodic table at this point really helps you know kind of where your electrons are and how many you have and all of that good kind of stuff. I always appreciate it when I didn't have to just straight up memorize, but I could connect it in, especially if I could connect it in to the periodic table, because I knew I would always have access to a periodic table whenever I took a chemistry test. It'd either be up on the wall or I'd have it right in front of me, or somewhere there would be a periodic table. So I really like to point out how the periodic table will give you a lot of this information so you don't have to just straight up memorize it. Okay. Next slide, although I've been doing a lot of back and forth. So when you're doing electron configurations, there are really 2 different ways to do this. So I'll show you the way that doesn't really work for me, and then I'll show you the way that works for me. So you might see this chart here in your textbook, and this tells you how to fill your orbitals. So you can see, you're just going to follow the arrows. You start with your 1s, and then you come back, and then you do your 2s, and you come back, and you do your 2p and your 3s. So you're just following this road here. Now, this absolutely 100% works, but I'll explain why it didn't work so great for me. It just didn't really mesh with how I thought. When I would try to memorize this, or if I felt like I had it memorized and I wrote it down on like a quiz or a test, I would invariably put some kind of mistake in. I would either put these guys, like I wouldn't get this P in the right place, or I would skip something, or I wouldn't follow the roadmap correctly, and then all of my electron configurations were wrong. So it didn't take me too long to figure out that this just didn't work very well with how I think. However, it works great for a lot of students. So if it works for you, absolutely use it. It will get you the right electron configuration. What I did was I like to use the periodic table, and that just worked so much better for me because I could see it and kind of fill it in my mind. So what I did was I would block out the different sections, and I'd say, okay, those are my S's. Here are my D's. Here are my P's. I did purposely not put helium in there. And then here are my F's. So I'll put that over here. And then I just used my numbers, my principal quantum numbers here, to know if I was talking about the 2p or the 3p. Well, if I was talking about phosphorus and I was doing that last electron, I knew it had to be in the 3p because it was in the 3rd row and it's in my p block. So for me, that just made a lot more sense, and it worked better with how I thought. Now, helium over here, and this is where you get variations in the periodic table. You might sometimes see helium written on this side, or sometimes you see hydrogen written on this side. So remember, in this, when n equals 1, you only have 1 orbital, you have 2 electrons, so you're only going to have hydrogen and helium. Now, helium physically matches better with your noble gases, which is why you tend to see it on the far right periodic table, but it is actually not part of that P block, so that is something that I want to point out. Okay, so now that we've spent a good half of the time knowing what our orbitals are and where they are and how many electrons, let's actually do some electron configurations. All right, so I just pulled up a really, really big periodic table here. It does mean that I'm going to have to write these electron configurations kind of small, and we'll have to do some erasing and going back. But I just wanted to make sure this was really clear. If as you're doing these and as you're watching me do these electron configurations, it will help if you have a periodic table like right in front of you, because then you'll be able to see it a little bit better too. All right, so I'm just going to go ahead and block off, like I did in that previous one, all of my orbitals. So these first two columns are my S. These guys in the middle are my D orbitals. These 6 at the end, excepting helium, of course, because it's special. These are my P's. And then these guys here are my F's. All right, so those are my different types of orbitals already blocked out. And you know what? Let me just put this in black because this periodic table doesn't have these numbered. I'm going to put my quantum numbers out here. 5, 6, 7. All right. Great. So, and this is how I would approach when I had to do tests with electron configurations. This is how I did my periodic table. All right, let's start with easy ones though, right? Let's start with the electron configuration for hydrogen because it has one electron and I find it's the easiest. So the first thing I want to write is its principal quantum number. Basically, what row is it in? Well, hydrogen is in the first row. So I'm just going to write a 1 down. Next, I want to say which orbital is that electron in? Is it an S, a P, a D, or an F? Well, it is in my block for the S's, so it is an S orbital. The next question I want to ask is how many electrons are in that 1s orbital for hydrogen? Well, hydrogen has one and only one electron, so there is one electron in that 1s orbital. So that becomes a superscript here. So this is the electron configuration for hydrogen. It has one electron, it is in the 1s orbital. You can see this is why we start with hydrogen. It's nice and easy, but let's just move forward really slowly and make sure that we get everything down that we need to. So let's do helium. Now, when you're first doing helium, it might be easier to think of helium being right here next to hydrogen. So I can do that. Let's put helium right here. Again, your periodic table might actually have helium written there, or sometimes you'll see them written both places. All right, so helium. What row am I in? I am in row 1. What orbital am I in? I am in the s orbital. How many electrons are in that s orbital? There are 1, 2, or sometimes I will actually cross that out. 1, 2. So I'm going to put a 2 here. All right, so that is the electron configuration for helium. It has 2 electrons. They are both in the 1s orbital. So this makes sense in terms of hydrogen and helium. They should have similar electron configurations, but they should not be the same, and they're not. They're both in the 1s, but hydrogen only has 1 electron and helium has 2. All right, let's keep going. Let's go to lithium. So lithium has 3 electrons. So we need to specify where those 3 electrons are. So once I get past hydrogen and helium, I always think to myself, I really am starting with that first electron. I'm starting with where hydrogen is on the periodic table. And it is in the first row, and it's starting in the s orbital because I'm in the s block. Now, then I count how many electrons or how many atoms do I see in that block, and I see 1, 2, and then that maxes me out. I can't put any more than 2 electrons in that 1s orbital, but I haven't gotten to lithium yet. Basically, I've marked out hydrogen and I've marked out helium, but now I've got to get to lithium. Well, lithium, we move down to our second row, so now I have a 2, but it's still in the s block, so it is the 2s. How many electrons? Well, it is in the first spot. There is one more electron, so I just write a 1 up here. Now, when you do these electron configurations, if you add up your superscripts, that should give you your number of electrons. Now, in terms of neutral atoms, that will add up to give you your atomic number. Ions, which we will not mess with, will not add up to give you your atomic number. But when you're talking about neutral atoms, remember your atomic number is your number of protons. It will equal your number of electrons. So you can see for lithium, I have 2 plus 1, which is 3, which is my atomic number. So that's a nice way to just check and make sure that you've accounted for all of the electrons in that atom. Let's keep going. Let's do beryllium. And I'm going to have to start erasing soon, but I think I can squeeze beryllium in here. Again, I always start in the upper left-hand corner of the periodic table, or you can think of always starting with hydrogen. You're starting in the first row. This is the s orbital. How many electrons? 1, 2. And then I'm done. I've got no more. I'm going to have to go down to the second row. So then I go to the second row. I am in the s orbital. So again, I think of this as kind of crossing off hydrogen and helium. I have done both of those electrons. Now I need to cross off this electron for in the space of lithium. There is 1 here, but I have another electron in beryllium. They're both in the s, so that's 1, 2. So that is 2s2. Again, if I were to add 2 plus 2, that gives me 4, which is the atomic number of beryllium. Okay, I'm going to have to make a little bit of space here. So as you practice these, what I really hope that you find is that there's a very strong pattern here, and then you can just follow the pattern for all your electron configurations. But to find the pattern, you have to kind of slog through doing these electron configurations kind of over and over again. This is why I'm just adding 1 more electron per electron configuration. Don't worry, I'm not going to go through all of, let's see, this periodic table actually gives me 118 elements. We will not be doing that tonight, but let's establish our pattern, and then we'll talk about our more complex electron configurations. And let me just make sure, okay, that there are no questions. So we did beryllium. Let's go on to boron next. So the electron configuration for boron, starting in the same place. I'm going to start in that 1s, that place where hydrogen is. So this is our 1s orbital. How many electrons? 1, 2. Now I'm going to have to switch quantum numbers. I'm going to have to switch orbitals. Now I go on to row 2. This is 2. I kind of come back to the s block almost. This is 2s. How many electrons? 1, 2. And I can't put any more. Remember, your s orbital, there's only one of them. You can only hold 2 electrons. This is why boron jumps all the way over here. You notice it goes from the s block to the p block. So these are now my p electrons. Are they 1p? Are they 2p? Are they 3p? I need to look at my row number. They're in row number 2, so these are 2p electrons. How many? Well, for boron, there's just 1 because there's just 1 spot here. Okay, let's go ahead and do carbon. I was going to skip ahead, but yeah, let's go ahead and do carbon. All right, so for carbon, again, we always start in the upper left. This is our 1s. How many electrons? 1, 2. And now I'm going to have to change orbitals. I have to go down to row number 2, but I'm still in the s's. So this is now 2s, and there are 1, 2 electrons. Now I skip across. I stay in the second row, but I skip across, and I'm trying to do carbon. So this is now my p block. It's my 2p block because I'm in row 2, and there are 1, 2 electrons here. And again, let's double check. So carbon has an atomic number of 6, so we should have 6 electrons here. So we have 2, 4, 6 electrons. Again, it's nice to get that confirmation. All right, I'm going to have to do some more erasing because, again, I don't have a lot of writing space up here. And how are we doing on time? All right, we're okay on time. All right, let's go ahead and let's do fluorine. So I'm going to skip ahead a little bit, but let's do fluorine. I'm starting in the same place that I did for all of the other ones, the 1s. How many electrons? 1, 2. And now I need to bump down to the 2s. Electrons, 1, 2. Those are full. I have to skip across to my 2 p's. And for fluorine, let's count across. 1, 2, 3, 4, 5. Fluorine has an atomic number of 9, so 2 plus 2 plus 5 is 9, so I have accounted for all of my electrons. Okay, let's skip neon. Let's go ahead and go down now to magnesium. So we're skipping quite a few here. Let's do magnesium. Starting in the same place with my 1s. 1s, how many electrons? 1, 2. Now I have to switch to my 2s. Count up my electrons. 1, 2. All right, so that takes me to beryllium. I have to keep going. Now I'm in my 2 p's. And I have 1, 2, 3, 4, 5, 6. And then I have to switch to a new orbital. I'm out of space here. So I'm switching to my 3rd row. I am back in the s's, so now this is the 3s. And for magnesium, I'm going to count 1, 2. So those last 2 electrons are in the 3s. Again, magnesium has an atomic number of 12. So 2 plus 2 plus 6 is 10, plus 2 more is 12. So again, they should all add up here. You'll notice that these are getting a little bit long, yes? But let's keep going, and then I'm going to show you a bit of a shortcut. Let's maybe do the electron configuration for argon next. And I'm going to need space, so I'm going to have to get rid of these guys. All right, so argon. Electron configuration. I'm going to have to deal with 18 electrons here. Okay, so, excuse me, that sneeze is going to come back later. I'm starting in the 1s. 1, 2. Go to the 2s. How many? 1, 2. And then I have to jump across to the p's. These are the 2 p's. How many? 1, 2, 3, 4, 5, 6. And then my 2 p's are full. I have to come down to my 3rd row. But coming back down here, I'm back in my s. How many? 1, 2. And then I'm out of space in my 3s, and I'm jumping all the way across back to my p's again, but these are my 3 p's. So 3p, and let's count across until we get to argon. 1, 2, 3, 4, 5, 6. And now we've hit argon, so we should have 18 electrons. So let's count up. 2 and 2 and 6 is 10, plus 2 more is 12, plus 6 more is 18. So those are my 18 electrons for argon. Now I'm going to add just one more. I'm going to go to potassium. All right, so electron configuration for potassium. Again, starting in my 1s. How many? 1, 2. Now I have to go down to my 2s. How many in my 2s? 1, 2. Jump across to your 2 p's. Count them up. 1, 2, 3, 4, 5, 6. 2 p's are full. I have to go across to my 3rd row, and this is going to be my 3s. How many in there? 1, 2. And then that is full, and I'm coming all the way across here to my aluminum. These are my 3 p's. How many? 1, 2, 3, 4, 5, 6. I'm not finished yet because I've only gotten to argon, but I've got to get to potassium, so I need to add one more electron, but my 3 p's are full. So I'm coming now down to my 4th row. This is quantum number 4. Again, I'm back in my S block, and I just need one more electron for potassium, so that is 4s1. Now, again, you can see these are starting to get long, but you can always write your electron configurations out this way, but you just start to write a lot of electrons, and at some point we don't need to see all of those electrons. So we do something called the noble gas shortcut. So if you take a look at your electron configuration for argon, you can find it within the electron configuration for potassium. So you can see that this whole electron configuration is found in potassium right here. So I'm going to rewrite the electron configuration for potassium, and I'm going to use argon as a shortcut. This is called the noble gas shortcut. So for potassium, let's see, I'm going to write it down here. I'm going to rewrite this as argon. in brackets, and then I just need to add in whatever is outside of those brackets. So this is 4s1. So what this tells the reader is, okay, electron configuration for potassium. I want you to find argon on the periodic table. You go, okay, I found argon, great. And I want you to then add the 4s1 electron. So you say, okay, I found argon, I'm going to add one more electron. Oh, okay, that's going to be potassium. Now, the thing to remember when using the noble gas shortcut is you have to use a noble gas. So if you're doing the electron configuration for selenium, you cannot tell the reader to go look at the electron configuration for arsenic and then just add one more. It must be one of the noble gases. Also, you have to choose a noble gas that I think of it that I've already passed. So like I found the electron configuration for argon within the electron configuration for potassium, but I would never be able to find the electron configuration for krypton within potassium because it doesn't have enough electrons. So I'll show this. This gets really tempting when you end up doing an electron configuration for a halogen because you really want to use that noble gas that it's next to, but you can't. Okay, so let's give myself a little bit of space. Great. Okay, so let's do bromine. So here we have the electron configuration for bromine. So the temptation here is to use krypton for your noble gas, but the problem is krypton has more electrons than bromine has, so you cannot use it. It must be a noble gas that has fewer electrons. So what is my closest noble gas that has fewer electrons? Well, that is going to be argon. So again, put it in brackets, and we're starting with argon, and my next orbital is going to be my 4s. All right, how many electrons? 1, 2. Next, I go across to my Ds, and if you remember, your Ds count back 1. So this is my 4th row, which means these are my 3 Ds. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, great. That's the end of my Ds. I am back in my P block. So it is important to keep this line right here in mind. Once you cross it, you have switched your orbitals. You've left the D orbitals. You are now in the P orbitals. Okay, so I'm in the P orbitals. And remember, your P orbitals do match up with your row here. So these are my 4 Ps. And let's count across. 1, 2, 3, 4, 5. And those are all of my electrons in bromine. Now, your counting up can still work. What you need to do is for this argon, you need to say, all right, you need to start with 18 electrons. So you can say I have 18 electrons, plus 2 is 20, plus 10 is 30, plus 5 is 35, and you can see bromine has an atomic number of 35. So you can still add up your electrons, just make sure you get your total number of electrons from your noble gas for the noble gas shortcut. Okay, we've got a little bit more time. We have seen here how the Ds work. Let's do another electron configuration with the Ds, and then we'll talk about the Fs. Okay, so I'm going to get bromine out of here so I just have more space. Okay. So let's do one that's nice smack dab in the middle of the Ds. Why don't we do silver? Ooh, actually, sorry. Silver is an exception, and we just don't have time to do the exception. Let's do one that's going to follow all of my rules. Let's go palladium. And it depends on your class and your teacher or your professor. Some just want you to predict just based on the rules and not do exceptions, and others will want you to do exceptions. So you'll have to check and see again with your teacher or your professor which one you're going to have to do. But let's do palladium here. All right. I do not want to start in the 1s because that's going to be a really long electron configuration. So I need to find my closest noble gas that does not have more electrons. It's got to have fewer electrons than palladium. So I can't use xenon because that has more electrons, so I'm going to use krypton. Again, put it in brackets. So that means, in essence, I am starting with krypton. My next orbital is going to be my 5s. All right, so how many electrons in my 5s? 1, 2. Next, I'm crossing into my Ds. Remember, your Ds count back 1. So instead of 5 Ds, these are 4 Ds. And let's count across to palladium. So 1, 2, 3, 4, 5, 6, 7, 8. And that is your electron configuration for palladium. So it really makes it a lot easier when you use your noble gas shortcut. Okay, now let's tackle some elements that have f orbitals. All right, see ya, palladium. Let's see. Let's do one of the ones that I'm a big fan of. Let's do berkelium down here because that is my alma mater. Okay, berkelium. It has 97 electrons, so this is really where you want to use that noble gas shortcut. All right, but I need to find an appropriate noble gas. So berkelium, it's going to land right in here. It's an actinide, so it's going to be right in this spot right here. So I need a noble gas with fewer electrons than berkelium, so I am going to use radon right here. Radon only has 86 electrons and berkelium has 97, so that's totally fine. So I'm going to put radon in brackets. Oops. All right, so starting at radon, I go to my next orbital, which is my 7s orbital. How many electrons? 1, 2. All right, here's where you want to be really careful to follow your atomic number. So let me just point this out before I continue. We've gone number 87, number 88, number 89, but whoa, what happened here? We switched over to number 104, so we lost some electrons there. You didn't actually lose them. These are your F electrons. They're right in here, and this is why the Fs are written down here. So in essence, your Ds are going to be split. So sometimes what I will do is I'm going to put a nice bright red line right here to remind myself that if I have to cross that line when I'm doing electron configurations, I need to add my Fs in. Because you can see up here with lanthanum is number 57 and hafnium is number 72. You lost 14 electrons. Well, you haven't really, but you've just skipped over your Fs down here. So again, however you want to note on your periodic table with a line, with a star, you saw on some of the other periodic tables, they actually pulled these two elements out to give you a hole to say, hey, something's up. Just remember, you're following atomic numbers here, and these are not sequential. Okay, so I have, so let me get back to my green. So I have 7s2, so I've taken care of all my electrons up to radium right here. That's number 88. I can go on to number 89. This is actinium. That's totally fine. This is in my D block, so it's not 7D. It is 6D. And I only have 1, and then I'm going to have to switch orbitals. So I'm just going to put 1 in right here. Again, I'm following my atomic numbers. So atomic number 90 comes down here to the Fs. So you remember your Ds count back 1. And if you remember, the other rule was your Fs count back 2. So these Fs are in row number 7, but they are not 7 Fs, they are 5 Fs. So these are my 5F electrons. And let's count across to berkelium. So 1, 2, 3, 4, 5, 6, 7, 8. And there's my electron configuration for berkelium. So this is why, if you've ever wondered why your Fs are down here, they kind of, you can't squash them all in that slot where I've drawn my red line. So that's why they pull them and they put them down at the bottom of the periodic table. Okay, I know we are almost out of time, but I want to do one more electron configuration. I consider these to be the most difficult electron configurations because it's easy to miss something in these. So let's do the electron configuration for lead. I know you're thinking, lead, shouldn't we be doing something more difficult? But trust me on this. All right, so I'm going to erase berkelium here. And now let's do the electron configuration for lead, because if you can do these guys down here comfortably, then you're probably very comfortable with your electron configurations. All right. Noble gas shortcut. I need a noble gas that's close to lead, but does not have more electrons. It's got to have fewer, so that's going to be xenon. So I'm going to put xenon in my brackets. So that means I am starting at xenon. My next orbital, I'm coming down to row number 6. I'm back in the S's. 6s, how many electrons? 1, 2. Okay, keep on going across. So I have crossed from my S's now into my D's. So these are my D electrons, and I remember that D's count back 1. So these are not 6 D's, these are 5 D's. Great. How many electrons? Well, okay, I just have 1, because again, I'm following my atomic numbers and I cannot just jump from 57 to 72. So I only have 1. That's my 5D1. Now I've got to go to another orbital. So if lanthanum is number 57, where is element number 58? It's right down here. It is cerium, but these are now in my F's. Again, I'm still here in row 6, but F's count back 2, so these are my 4F. And how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, which is what you would expect, right? F has 7 orbitals, 14 electrons. Again, this is why you don't have to memorize it. You can just count from the periodic table. That's an aside. Okay, that gives me to atomic number 71. Where is my element with atomic number 72? That is hafnium right here. So I have switched orbitals again. I am no longer in the F's. I am in the D's. Well, which D's am I in? I'm in row 6. I'm back in my 5Ds. Let's count up electrons. Remember, start at hafnium. You've already counted that electron from lanthanum. So starting with hafnium, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's it for my Ds, right? Because once I cross this line, I'm now back in my P block. So I have switched orbitals. So these are my P's. These are my 6 P's. I'm going over to lead, so I have 1, 2 electrons. And that is your electron configuration for lead. Before I sign off, I know we are definitely running out of time here. I do want to point out that while I have written the electron configuration like this, you will see it written different ways. So a lot of people like to combine the 5Ds, so they'll write 5D10. Other times you will find these written according to your quantum number. So I'll just show you a couple different variations here before I finish up. So first I'll show you with just combining the D's. So that would just be 6s2, 5d10, again 1 plus 9 is 10, 4f14, 6p2, which is totally fine. Until you're really comfortable, I caution you for just writing this out like this, because again, it's very easy to miss this line and you're going to miss those 14 4F electrons, and that is going to be an incorrect electron configuration. Okay, so what you will also see is this will be written like 654, like so. So again, electron configuration for lead, xenon. So some like to combine everything, your 6 quantum numbers together, 6p2, and then it'd be 5d10 and 4f14. Again, totally valid. You can put it in whatever order you want. And other times, instead of counting 6, 5, 4, you'll count 4, 5, 6. So there's one more. I'm really running out of space. Maybe I can squeeze it in over here. You might also see it written as 4f14, then 5d10, that is a 10, then 6s2 and 6p2. It doesn't make a difference because you have specified where all the electrons are. This is where it matters what either your teacher or your professor wants you to do, and you follow that rule. But you might see them written in different orders. They're all perfectly valid. All right, well, I hope you found this helpful with the quantum numbers and the electron configurations. And, give me a shout out either by email or in comments on Facebook or YouTube, and let me know if you'd like me to cover something else. Thanks so much. Bye.